the Brazilian Statistical Association and the ISI um, planned this session as a joint session. And our speakers here, they kindly accepted to take part in one more session in the conference because they were already presenting short course and conference and other thematic sessions, but they agreed to join us in this discussion. The session will be quite easygoing in the sense of structure because they preferred to have it as a panel session where we agreed 4 or 5 questions, and then we'll start one of the questions, and then our invited speakers will start with their views on it, and we hope that the audience will also join us together here. We also have Professor Alan Gresti, Professor David Spiegelhalter, Professor Fabrizio, and Professor Hugh Jerry, and Professor William Meeker. And in the audience, we also have Professor Michael Kozorok, that is here as an invited speaker of the conference as well. I won't introduce all of them again because they have already been in other sessions, and we all know that we are honored to have them here as invited speakers. And I will just say the objective of the session is a panel, in fact, to discuss the areas of application, barriers, and opportunities for expanding statistical practice. That is the focus for the next 10 years, 15 years, considering the problems that may drive the development of new models, methods, and ideas in statistical methodology. So I will start with the first question that has been agreed, that applications for areas of statistics, and we ask them, so please pretend you are an Earth explorers thinking about our planet. Statistics has gone everywhere, or almost. Where should we go next? So I hope someone will volunteer to start. Ta-da. No? No? So, Fabrizio? Yeah. Someone has to start. I'm so sorry. I'm the boss. So get it. Do it.
I'll say a couple of words. Can this come on here? Hello? Oh, thank you. So where do we go next? As I was thinking about that question, I felt that, we've been to lots of places before, but I don't feel like I'm in the driver's seat or even in the seat where I can direct the direction. I think we sort of have to look at where the needs are and what new problems are arising in practice, and that's where we need to go. It's not anything in particular that I can see. So from my own discipline, which is engineering applications of statistics, one of the things that I mentioned in my presentation the other day is that the nature of the data that we see coming from the field has and is changing dramatically because of big data. That is, systems are collecting and reporting data at intervals of time like every 10 minutes, and they're reporting large vectors of data potentially. And so, so we as statisticians working in these areas have to be thinking about and developing appropriate methods to take most advantage of those data that are now being collected. And we can see the same kinds of things happening in virtually every area of science and engineering. So that's, and we'll talk later, I think, in this session about big data, and so that's certainly an important area.
What I'm going to say is about some examples. I think we are almost everywhere, as Denise said. The problem is that we have to be everywhere in a better way and also to be recognized. There are some examples, I think, of cases in which emotions, political issues, superstition and other are ruling the most. I think statistics should be used to assess more scientific approaches to things. And examples, and I have in mind, one is about the genetic modified organisms. I don't know if you are aware that recently in May, the National Academy of Sciences of the United States published a 700 pages report on the influence of GMO on the health of the people. They compare the behavior, the health of people in the United States and health of people in Europe. In the United States, people have been exposed to GMO a lot. In Europe, not much because of, as I said, political pressure by the public opinion and so on. And the findings of these people, these scientists, were not paid neither by Monsanto nor by the people selling biological food. So we were independent people with different background, I guess also a lot of statisticians inside that. The finding was that there was no evidence saying that the GMO are affecting the health of the people. So, as I said, so there is a political issue here, some pressure by different groups, and I think science and statistics in particular can give a contribution. As another example, in Italy we have a city called Taranto, where there is a steel factory, and the issue here is the steel factory increasing the number of tumors in the city? And there are epidemiologists working on both sides, the environmental side and the company side. I know very well both of them, and they're coming up with different conclusions. So here is an issue about statistics. Can we squeeze statistics also in one direction or in another? Also, in this city is an important problem because on one side there is the health of the people, but on the other side, the economy of the city relies a lot, especially on this steel factory. So there are two different components. So the point is, in my opinion, the target, the goal of our work is try to use statistics to address problems. Another important problem is experiments with animals. In Italy, we have some people sometimes attacking laboratories and freeing animals, claiming that research on animals is useless. Everything can be done without experimenting on animals, but just by using models. Well, speaking with people, I would say it's not possible right now. But that is one of the possibility offered to statistics. We can be very helpful. Already statistics is helpful in this direction, trying to reduce the number of animals involved in this experiment. So there are a lot of issues in the society related to politics, to public opinion, which could be addressed in a more scientific approach, and that is one, I would say, one of our goals for the future for us as a statistician.
Yes, I'd just like to build on the previous two comments. I do see there's two directions being identified. One is to do with data, and we'll come to big data, but the huge amounts that are coming online from many different areas, and in that sense, we can't say, we just have to be responsive. Statistics is people say it's an enabling technology. It helps other people to do things. And so we have to be ready to dive into areas when they come up, and to be flexible and innovative and fast moving, agile. But the other aspect which Fabrizio described is the fact that statisticians are also experts on evidence, not just data, evidence. What does this data mean? What can we learn from it? That's where our real expertise comes, beyond manipulation and computing. Our expertise is in evaluating evidence. And for that, there's plenty of work to do in current areas where we are not having objective or at least balanced interpretation of evidence is not present. We mentioned GMOs, of course, but there are other areas, electromagnetic fields from mobile phone radiation. Recently, a huge experiment done in the US, using the standard toxicological designs And I looked at them and I thought, this is terrible. This is really bad. This just doesn't seem very good statistics at all. But that's what is done in that area. And there are so many different areas where they've grown up a particular practice that has not really been open to external scrutiny. People do certain things in toxicology and other areas. And statisticians need to get in there and have impact. And that's why I think communication is so important.
Yes, building on David's comments, I think another example, I'm thinking here in the United States particularly, such an important issue as global warming. It would be great to see statisticians having some impact in analyzing the available data and trying to make people understand what is really happening. And we have one of our two main political parties in the U.S. that even denies there is such a thing as global warming. It's not an easy issue to talk to some people about, but it's just obviously an extremely important issue worldwide where I would hope statistics could be having an influence on things like this, just generally public health issues, having somehow our input be valued and communicated to people in an effective manner so we can have some effect. Otherwise, I would just say we don't necessarily have to go exploring. I just think of myself, being an old guy here, and what's happened over the years I've been a statistician. I think back when I was a graduate student, and a lot of the areas that are now so important didn't even exist. Something like survival analysis. Okay, suddenly people are seeing sensor data and missing data, and statisticians being driven to move into new areas like that because there are data that we see like that all the time, and realize that we have to come up with some way of treating it. So I think probably that sort of thing will happen in ways that maybe we don't realize right now. There will be, with the increasing types of data becoming available, things we don't even consider yet that'll be important to us sometime in the future.
Thank you. Is there anyone in the audience who would want to suggest or add a comment to this point? No? Some of the issues that we have been commenting now will be also in other questions like big data and sustainable development goals and other sessions. So the next one that we want to focus is statistical education. We know we have to, the development comes from research, but the use comes from teaching in every aspect, not only teaching in undergraduates or postgraduates, but teaching the society and teaching professionals to work as statisticians. So I would like to listen this from the speakers.
Well, I'll be happy to start off here if you like. Most of my career at the University of Florida, I spent a lot of time teaching statistics 101 sorts of courses to general audiences or social scientists, and I've seen some real improvement here for teaching, in the sense that when I started, a typical intro stat course and a typical textbook was just watered down mathematical statistics, sort of showing basic results we would see in a math stat course without the calculus, but not much focus on the concepts, more on recipes and theorems and what the formulas are, and not so much on interpretations and assumptions and what things are like in the real world. So I think there's been at least what I see, there's been tremendous improvement in the last 40 years in terms of what is in our basic statistics courses. The more emphasis on concepts, starting with books by people like David Moore, more real data instead of artificial examples. But a challenge that I think is still really there, that hasn't really improved, is that you look at the great amount of statistics teaching going on, which is in the US has been increasing all the time as we now have courses at the high school level that are very popular. The percentage of people teaching these courses with a good background in statistics is small. Even at the university level, most courses are not taught by statisticians, often by mathematicians, who again will just teach it as a watered down math stat course, or by people in sociology or psychology or whatever that may, that have good intentions and sometimes really good training, but often have only had one or two courses themselves as graduate students. And so it's a real challenge. We all know increasingly, I think, as we get older, what a tough subject statistics is and how even basic concepts like sampling distributions aren't so easy to teach. So in the US, I see as a continuing challenge that we have a huge number of courses. We need to do a lot more work in terms of trying to train people to reach levels where they can teach these courses in a useful manner. Luckily, there are more things available to help with that, such as online applets and uh, new ways of being able to teach old concepts that are more effective. So there's certainly a lot of scope for improvement in the future, but it still is a real challenge.
I think this is a fascinating time for statistics education, very exciting indeed. But we have to recognize there are different audiences. I teach maths undergraduates. Standard, first lecture, probability revision, second lecture begins, let x1 to xn be IID, random variables from a normal, etc., etc. So as soon as you are thinking in terms of x1 to xn be, IID, random variables, that, as Alan was saying, is fine for some audiences, but it's just got to go for most audiences, I think. So my feeling is that although Alan says this is happening already, that statistics has to, essentially, mentally separate from mathematics and engage with data science and computer science much more. And I just feel that's a move that must happen. For general statistics education, not for the math students. They're fine, and you need them. There have to be people who do know x1 to xn be IID. There have to be people who know those results. A really good, solid core, absolutely vital. But the vast numbers people being taught, I don't know, Auckland University, their first year, there are 4,000 students doing their stats courses every year coming in. So with that sort of industrial scale statistics teaching, you have to change and you have to move along the areas which Alan was saying, and particularly the ASA have got these GAZE guidelines now, which I think are tremendous on teaching statistics, which are all to do with real world data, serious attention to computing, answering real questions. And I'd say in particular, an interest in simulation-based inference, so that when we're looking at sampling distributions of statistics, which is the most difficult thing in statistics, and it is really difficult to teach, it's difficult to understand, let alone teach. And many innovative teachers now, for example, in New Zealand, start off by doing that with bootstrapping. And the actual mathematical, the closed form distributions for test statistics is taught right at the end of the course. So I think those sorts of innovations really should be taken very seriously.
When I think about statistics education, I like to think about the three different groups that we need to address. In our department, we have an undergraduate program, we have a graduate program, and then we've got the service teaching, which is the big one, and that's really what everybody else was referring to, because that's the huge audience that we have in terms of number of students that we see every year. But the concerns are a little bit different in those different categories. I think for obvious reasons that David was alluding to, that some have more mathematical backgrounds and the others really won't, but they still need to appreciate the basic concepts of statistics. There are two things that I think are important as we design our educational programs in statistics that go across those groups. One is curriculum. What is it that we're going to teach? I remember about 20 years ago in our department, some of us sort of looked back at the history of what had been taught in the department going back to the 1950s, and here we are in the 1990s, and we're looking at the topics in the courses 30 years earlier, and they hadn't changed. They really hadn't changed. And so we began to think about, okay, what do we need to do to make things more modern? And we've done that, and we do this now more or less continuously. So for example, I think we've all recognized that we need to get a lot more computing into the curriculum and have it integrated into all of the courses, both the theory courses at some level, that is, for our undergraduate theory courses, we integrate some computing because it's helpful for students. And certainly in the methods courses, we have computing very deeply integrated, but even as we progress and get more and more computing power, that's going to again shift the way we teach. The other thing that I think is important is the other thing that I think is really important is to emphasize by using relevant examples, again, at all levels. We just watched Alan give this wonderful short course this morning on categorical data, and mixed in with all the technology were a whole series of really beautiful examples that illustrate the importance of the methods.
Well, I'm not in a university, I am in a research institution, but I have been teaching quite a lot, but I would like to contribute also some other different points with respect to the other colleagues. But the first one, it comes to me naturally and quite expected from my background. I would say that in many basic courses there is something which is definitely missing, the Bayesian approach. I think this is a natural way of thinking in everyday life. When I start courses, I always make an example about saying that everyone every day is a Bayesian in the daily life. So, but that is missing in most of this statistics 101. But I would like to think of other three aspects. The first one is related to the organizer of this session, the International Statistical Institute, and its mission. I would say some words which are strictly related to statistical education as well. I am a council member, so I am a sort of representative here of ISI. And the mission of ISI is about capacity building. These are a couple of words which appeared some years ago and are very, very, very important in the mission of ISI. And using the expertise of people from more developed countries and go into developing countries and giving courses, mentoring people there. So this is an important aspect of statistical education. Bringing people where they are needed, where there is a need in Africa, for example, or also bringing people from Africa, Latin America to conferences and meet people important, which have a lot of share with them. And there are a lot of programs within the ISI. And for example, the World Bank is giving a lot of money to people, to young people, to attend from developing country to attend our meetings. Also, next one in Morocco next year. Also, ISI is organizing through its regional association and also the association which is related with a lot of activities in Asia, Far East Asia, Latin America, and so on. So there is this issue of education in developing country and the contribution that, for example, ISI can give. Also, there is an issue of continuing education for the people who are in companies. Once we went in Italy to work with a company which was one of the leaders in production of washing machine, fridge, refrigerators in Europe, and they had no idea what quality control was. We introduced control chart in that company. So there is a need of an increased statistical knowledge in companies, people who are already out of university, and we can do something like that. Also, there is some attempt by ISA, other association, to do accreditation. So the people are going around the world selling themselves as a sort of statistician have to be accredited by some reasonable association. So this is another issue. And finally, there is an issue about high school. This is an experience. My wife is now an high school teacher in mathematics, and I've been working a lot with her and with our students last year in creating a Bayesian belief networks. So the students had to think in terms of utilities, in terms of probability, in terms of a lot of stuff. In Italy, up to a few years ago, there was no probability, no statistics in the curriculum at high school level. And many professors nowadays are still not able to teach statistics properly because they were used to do trigonometry, solids, and other stuff. So there is a need to work on that. There are a lot of resources online, for example, from Khan Academy and other flips something. So that's another important part in which we should work on. Providing resources for high school teachers, because the knowledge of statistics and probability starts there, even earlier.
Um, since some of the speakers talked about you talked about accreditation and this, would you and some of the speakers come from countries where there is accreditation, or would you like to say something about it, if you agree, if you want to, you think the importance for the professionals? Can someone? There are
No, I don't
statistical
know.
society has
Yes,
some
yeah. Oh, I
accreditation.
should
What do
know.
you?
Oh, God, I suppose I should know about that. No, I don't know anything about accreditation.
But it's something that the professionals there do. Do you think they? Because I think they train also. It's an important issue sometimes because they people from other countries like African countries take the exams and then
Yeah,
it's
the Royal
important.
Statistical Society is stopping doing exams.
I stop it.
Stopping exams.
Okay.
Yeah. So it's no, I think it's a real problem because statistics and probability are difficult to teach. They are difficult subjects. People find them very challenging. So I think we use materials and training for teachers at schools and in universities is very, very important. But I don't know about formal accreditation.
So we will have time for questions that are not proposed here, but we would like to say if anyone from audience would like to liaise with this topic about statistical education in our degrees in Brazil. Some comments? No? Some comments in Portuguese? Yes, of course. Yeah, whatever. Feel free.
Well, I just would like to ask you one question about the first topic, which is the uh, that I believe that several research nowadays uh, denominate themselves data scientists. I mean, there are what you can think as a new area related to this topic. And I just like to get the opinion from you that will be a place for statisticians in this kind of world, or we will become in a moment data scientists as well. So that's the question.
That's the next question.
So thank you. You're just introducing.
just-
Great. Thank you very
yeah.
much. You're just introducing the next topic.
Perfect
Ah,
introduction.
no, but it's okay. It's
Yeah.
perfect.
Yeah.
Because that's what we wanted. We wanted that people would talk with with the audience. And then we only have one more topic after that, and then others will pop in the audience. So following your suggestion, we just get this that it's about data science, machine learning, data mining, and are we going to succumb to computer power? Why and why not? And is it a time for more or less statistical thinking and statistical methods together with this data revolution and data science and all of this that we are living now? Thank you.
You go first. Oh,
Go ahead.
Okay.
yeah, okay. Yeah,
So,
yeah.
well, you skipped this question. I was ready for the other one. Okay, data science. Well, in my experience, I've been always finding some strange word buzzwords. It was Six Sigma, and then machine learning, and then data science, and the point is, was providing this data? Sorry, these words, and Well, Six Sigma, I don't know if you are aware of this one, is a way some engineers, consultants, and so on are trying to sell Statistical 101, stealing our job. Machine learning, well, from my point of view, is another way of stealing a little bit of our job. Also, data science is that was my first impression. But with the days going on, I thought, well, maybe it's not exactly that way. So I started thinking about data science. Well, it's a lot of statistics, but it's essentially what we have been saying for decades. It's in Italian, we say it's a discovery of the hot water. I probably is the same in Portuguese. What we've been doing for many, many decades. The other day, I was presenting a lot of examples about stochastic differential equations and cooperation between me, Bayesian statistician, my colleague, applied probabilist, a biologist, an engineer, an epidemiologist, a medical doctor, and so on. So, and also this work is something that we have been doing for ages. My question here actually is not an answer. I have a question. What is the difference with respect to what we have been doing in the past? I think we are very bad in promoting our expertise. We are maybe probably somehow a little bit snobbish in the sense that, well, computations, who care? They are just. But the point is that we have to be probably less snobbish, but on the other side, we have to fight and show that, well, statistics done by the statistician is the best one, not done by the computer scientist. So that is essentially my reaction when I see this. But we have to somehow to fight. For example, in the Bayesian community, they are giving too much power to the people in machine learning, but it's Bayesian non-parametrics, most of this. And we should have to keep it. And somehow, that's it.
Sorry, can I join in here? This is just the most important debate. I'm on the optimistic side. I think this is an enormous opportunity for statistical thinking in our profession. I see it very positively indeed. And the first thing is, I think we can't expect to keep Bayesian non-parametrics to ourselves. We should give it out to the world. Take it. Use it. We should be generous and open and inviting. At the same time, we must be strong and positive about what we can contribute. And again, I'd like to come back to this unique contribution that statisticians have, which is in terms of evidence. It's not just data. It's not just machine learning and deep learning. You know, they don't care about evidence. They don't care about second order properties or errors or p-values. It's technology. They want an answer, something that will do a good classifier, something that will be able to read your movements as you move in front of cameras. All that is fantastic work. It uses data, but it's not using evidence in the same way to learn about the world. And that is what our expertise is. So I see that the engagement with data science, machine learning, and so on can only be a good thing. And when it works, for example, the Bayesian non-parametrics, in the UK, I think we've been very successful in that partly because the statisticians have made friends with the machine learners with a lot of mutual respect. Okay, they stole Bayesian non-parametrics, but we say it's like giving you're giving something to a member of the family. You like to donate the tools, yeah, and so you remain friends. So that, for example, there've been big funding in the UK for the Alan Turing Institute, which is the data science big data institute in London, and which is headed by a machine learner who is a big friend of statistics. But the second layer of directors are almost all statisticians. The statisticians have got in there. For Cambridge, the statisticians wrote the proposal that made us part of the institute. So I think, by just saying, well, we can contribute and getting, not and being bold and being open, that we can be part of this development. And it's just so exciting. But we do have to tell people that, it's so, there are some idiots who think, oh, because we've got lots of data, we don't need statistical methods anymore. The data will tell us. And this is such nonsense, such really, when I've been interviewed about this, I've used a very rude word, which got published in the Financial Times. So, but essentially what I said was that many people are saying that the problems that we know about statistics, most of them get worse if you've got lots of data, get more difficult. The only one that doesn't get more difficult is the size of your confidence interval. But that almost certainly is wrong anyway, because your data is biased. And so all the issues about bias, about regression to the mean, about multiple testing or false positives, all these issues, which are real data statistics challenges, get worse when you've got more data. Correlation and causation, interpreting causation, they all get worse. So we have got even more work to do. So I see this as a fantastic opportunity. Data science. But will that involve statisticians? Yeah. I mean, Warwick has been, again, one of the main centres for, for statistical analysis of big data and part of the Alan Turing Institute. So, no, I think, that's what you've got to do. So, similarly in Berkeley, the wonderful course for data science. Berkeley, I think, is the place to look at for their data science. It's a really strong program, but thought jointly between computer science and statistics. And because people like Mike Jordan, who are joint appointments between computer science and statistics, have been in there, they've produced a course, it's a fantastic course on statistics for data scientists, which is, which is a stats course. But it's tied up with computing immediately. It uses simulation-based inferences very early on. But its very first lecture is about John Snow and interpreting cholera deaths in London in the 19th century. So they start off with a statistical evidence chat problem right at the beginning of the course. So I think if you really want to see what can be done, you should look at what they're doing in Berkeley.
Yeah, I can't really add anything important to what the other speakers have said here, but I would like to raise a related question. As our field incorporates more computer science, as we connect with data scientists and do all these new challenges, and as our own methodology continues to explode, we have more and more courses on different topics. What is the core of what we think of as statistics? What's the core material that we think all statisticians should know when we look both at theory and methodology? If you think of a PhD program, for instance, I think back to what I took as a graduate student, and some things that seemed very important then maybe aren't. I can remember old theorems from Berkeley in the 40s about uniform minimum variance unbiased estimation, for instance. That
I still teach that.
So, I mean, there's stuff that back then was the core to theory that probably isn't so much now, but we should have some identity as a field. My own sense is a lot of it's going to be what Fisher was saying back in the 1920s, but both in terms of the theory and the methodology, can we come to some agreement on things that should remain in essentially any student's program, realizing that after that they're going to move in all sorts of different directions these days? Can we maintain some identity as a field, at least in that way? I'd be curious to see what any of you or other panelists have to say about that.
So I feel it's fair to say that today, in many places, we have this unfortunate tension between statistics on one hand and machine learning or data science on the other hand. But if you look at certain historical things, and I'm going to tell a little story here in a minute, I'm going to make a bold prediction that 20 years from now, we won't have the tension and the turf wars that we're seeing today. That 20 years from now, there will have been emerging. We're in a time of change now. Things are a little bit turbulent, but I think 20 years from now, things will look different. What is it that leads me to this bold prediction? Let me tell you an historical story of something that to me seems to be very much parallel to what we're seeing now with this tension between machine learning and statistics. Back in the 1980s, there was a virtual revolution in the way that we view quality, the statistics of quality. And that revolution came from an engineer from Japan by the name of Junichi Taguchi. In the 1960s and the 1970s, Junichi Taguchi developed a system for improving quality, which was much different than anything that was being used in the Western world. And he sold that approach in Japan and in India very successfully. I'll try and paint a very simplified version of what Taguchi brought to the world of quality. When I studied response surface methodology in the 1970s, it was all about estimating the mean as a function of the X variables. What Taguchi did was he developed a system for reducing the transmission of variability. Very fundamental concept in theory, but also a very fundamental concept in quality. Because we're trying to produce a product, and we've got a process that does that, and the process has inputs, and those inputs are variable. And because there's variability in the inputs, we're going to see variability in the outputs. And variability is the enemy of quality, because you've got good and bad and some in the middle, and what you'd like to have is everything good, right? Taguchi developed a system to allow engineers to design the product and the manufacturing processes. It was basically a system of experimental design and a little bit of inference and then some optimization, putting all those ideas together to achieve much better quality. And in the 1980s, Taguchi decided he wanted to come to the United States to sell his ideas, literally sell his ideas. And I was visiting Bell Laboratories at the time, and so his entree into the United States was he invited himself, in so many words, to revisit Bell Labs. He had visited Bell Labs in the 1950s to come and introduce these methods. And I can remember going to his lectures, and it was very frustrating because he would not explain what was going on. He would say, this is what you do, A, B, C, D, and we had written books and so forth on this. And there were some very smart people in the room at Bell Labs trying to figure out what's going on. And I can remember my supervisor telling me one evening, we just can't, I went to some of these lectures, we just can't figure out if Taguchi is a genius or a charlatan. Well, eventually we figured out that he had something, but he was very rigid. And so what happened subsequently is Taguchi set up consulting organizations in and around Detroit, Michigan, which is the center or was the center of automobile manufacturing. And he was going to the different automobile companies and saying, I can give you what you need to compete with the Japanese. Because in the 1980s, we all came to realize, those of us who are objective about it, that the Japanese had much better quality and reliability in their automobiles. The Japanese had already shut down many industries in the United States, consumer electronics, optics, and so forth. They were gone. And the Japanese and others had taken over because of their high quality, high reliability, high productivity, and relatively low prices. And the same thing was happening in the automobile world. And Taguchi said, I can show you how to do this. And so many companies sort of bought into this. And it led to what was known, particularly in the automobile industry, as Taguchi Wars. And the Taguchi Wars were between the engineers who were taking the Taguchi courses and the statisticians who were trying to improve quality. And it was very, very uncomfortable for statisticians in the automobile industry in the late 1980s and the very early 1990s. So it was a very similar kind of thing, in some sense, to what we see. I remember being invited to a conference at Ford Motor Company by a statistician who was a very smart statistician. He looked at this and said, I think there's some real value in Taguchi, but we've also got statistical methods. What we need is a coming together. So statistician's name was Tim Davis. Tim was from the UK originally, but he was working for Ford in the Detroit area. And Tim organized a 2-day workshop where he invited people from both sides to come in and present their story, where we should do. And basically, Tim, I think, organized within the Ford Motor Company a methodology combining the best of both worlds that I think had a fairly substantially positive effect on the quality and reliability within Ford. And I think other companies were beginning to do the same thing. Fast forward 20 years, even 10 years later, there was this coming together. Nobody disputes the value of what Taguchi brought to the table. And it's been integrated now with statistical methods. And if you take a good course in response surface methodology, you'll be focusing on the mean and the variance. You'll look at how the variance changes. So it had a fundamental change in the way we do manufacturing quality. And so I predict that we'll see this coming together because there is truly value in some of the machine learning techniques. Now, some of these machine learning techniques, when you see them, I was just quoting to somebody who said, oh, well, there's a different vocabulary over here. This is one of my former students who was working in this area of data science now. When I say one of my former students, he was not a statistics major, he was a business major, but now he's working in business analytics. And he said, I've got some questions for you, Professor Meeker, could you help me? And he asked me all these questions, and all the questions were in the language of machine learning. And so I said, well, we've got a vocabulary problem here. I said, learning is what I call estimation, right? And on and on. And I said, and here's some terms I don't even know, although I Googled and I figured out what they were. And so we need to have really a coming together. Sorry for the long dissertation, but that's what I predict is going to happen.
Someone want to liaise that?
Thank you for the nice discussion. My name is Nikolai Kolev. I'm professor in University of Sao Paulo. How to say, data science and machine learning. Data science and machine learning are growing very fast. So statistics have to run to help data science, to help machine learning. How? At first, I do believe that we have to forget many axioms in statistics. Because data science, machine learning, they just show that the world is not normal. Any book in statistics begins with the basic assumption that we have a normal population. The population is not normal. Okay, in some limiting case, when n is going to infinity, when n is going to infinity, nobody knows. I loved your comment about Taguchi's contribution, but also I know that, for example, in Germany, they use already, also in the United States, they use standards which are different than ISO standards. this means that somehow the statistics to serve to data science, machine learning have to be simplified somehow. All laws we know, the normal law, F, T, chi square, they're based on the assumption of the normal population. And if the population is not normal, what happens? So I think that exactly engineers, the computer science experts would help statisticians to find the right way, because there is data analytics. These people, in fact, they have a lot of statistical programs. They do not need too many statisticians. They do their data science, machine learning without statisticians. So I think we statisticians have to understand, even to learn a little bit more data science and machine learning. Somehow, this is a point of revolution in our mind. Okay, this is my observations are more philosophical, but I feel that if we try to generalize and extend, etc., all existing models, we have zero chance to attend the data science and machine learning. Okay, this was my observation. Thank you.
I think as a statistician, we should use a couple of words to sell our job. Stochastic modeling. This is something that we can do better than everyone else. It's not just a matter of pushing a button. So what we have also related to education, we have to prepare people who are not only able to prove theorems, but also people who are able to start from the knowledge we have of, for example, stochastic processes and so on, and see what are the problems in engineers, in chemistry, and so on, and finding through discussion with engineers and so on, what are the best models. So we have to be, that is our contribution. We cannot contribute in terms of computation. Well, there is computational statistics, which is important, of course. I hear some people so I should be very careful about that. But I would say stochastic modeling. This is our selling word, I would say.
Yes, but before that, you have to explain what stochastic modeling means to the small boy. This is very complicated word.
I know.
Very complicated. Very complicated. I think.
So I'll comment that I agree that we as statisticians really need to understand what is happening in the machine learning world. And in our department, and I'm not directly involved in this, but we have two different courses in machine learning, one at a fairly high level, one at a slightly lower level, and they've been very popular courses because there's some very important tools there. And it's very important that we understand the relationship between what we're doing in statistics and what is happening in machine learning. And as I said, I think that eventually there'll be a coming together. In our department, we already have one joint appointee between statistics and computer science. We're looking forward to getting another, and I think those kinds of connections are very healthy as well to help this bringing together.
Only to add a sentence, for example, it is very important after you have been in Bell companies, you should know that there exists coding decoding theory of Jorma Rusanen. So coding decoding is something very important, and coding decoding should enter and should be explained to the small boys that will understand this much easier, how to transform your data in binary code and back, than to explain them what is stochastic analysis. Okay, this was my observation.
There is one there.
Hello, and thank you for the speech. It was lovely. I want to know, in the world, how fast the universities the professionals that are teaching statistics are accompanying the trends in the world, like data science, machine learning. How fast do you think the professionals are can change the way they are seeing and teaching the statistics, molding to the new techniques and methods that are always revealing in the academic way and professional world?
Well, I think it is such an important point is that, you know, if we can say that people should understand these things and we should be joining together, but unless, as Bill mentioned, unless the staff, you know, actually know what they're talking about, and it's likely now that, you know, many students will know more about these topics than the lecturers in the department will. But I can't speak because the course I'm giving is exactly the same as the one I did 40 years ago. So I'm not proud of this at all. But these are Cambridge mathematicians. They can deal with it. But afterwards they go on to be offered much, you know, better courses of advanced statistics that really are integrated up with machine learning courses. But it does mean then that the students are learning things that most of the staff in the stats department themselves don't understand. And I think that's a problem. You know, I think that is a problem.
Thank you for your speech. They are all of them. They very enlightening. Another thing that we have to take in consideration is that we have the same time to learn, to teach our students, and the world is changing. So stochastic modeling, as Professor Nikolai mentioned, it's extremely complicated to understand and to teach. And as Guilherme commented, we have so much to learn in machine learning, in stochastic modeling. Everything it's getting like a roller coaster. It's getting higher and higher and higher what we have to learn, and we have the same amount of time. So, on one hand, we should know everything. On the other hand, we cannot learn everything. So there must be a balance between what we know about stochastic modeling and what we know about machine learning, because we cannot understand everything in both fields. So I think the rate we professionals in academia should develop, it's not like linear. Well, there's development in stochastic modeling and there's development in machine learning. So we must learn both. It's not possible. So it's a very delicate issue, because we are talking here, Professor was saying that he teaches the same course he taught 40 years ago. So most of us do that. Like what Professor taught 40 years ago, we're still teaching. So it's very complicated to try to put more things in there, and we have a very complicated basis to cover, as Professor Nikolai was saying, because probability, inference, everything, it's not easy to teach. So there's this issue that must be very well thought. What is the balance between stochastic modeling and in learning theory and machine learning we should give to our students and the professionals? It's not possible to just learn everything. It's more like a comment than anything else.
I would join with a comment as well. We have just we had a discussion here on Saturday, on Sunday afternoon, with teachers and heads of undergraduate degrees in Brazil. And one of the things that we realized that many faculties or universities are changing their the way their degrees are now, with new disciplines to adapt to this new world. And this happened for at least 4 presents there were making this. So we have more on statistical computing, databases, introduction to programming, and things like that to make sure that we are we are making them able. So I teach in a faculty that is a small faculty, and we had someone with a PhD in computing to teach databases and things like that, because his view, we had at least for this year, but he's a collaborator or a visitor. And I understand that one of the things that we are feeling, I believe, is that we have to adapt, we have to teach, and and we have some time to adapt, but not as a teachers. As teachers, we don't have any time. You have to do it because you get someone in the first year course and an undergraduate first year. We can't wait until he or she is in the third year to say, by the way, during this time, all this have happened, and I have to, yeah, and you missed this part. So these students now are already entering our course, wanting and waiting for a course that talks with the data science and data revolution uh, ambience. So we will have to adapt, or we will have to join with other areas to make some of our disciplines keep the structure and keep the basics and the theory, but have them involved in this new world. We can wait, but they cannot. That's the truth. So I will move for the next one of the next questions. That is, oh, I did it the wrong way. Um, Thinking about now that also Fabrizio has talked about um, cases that, and I think more than one speaker talked about environmental issues in our first question. And it is, that's what we are living now in the world. The United Nations is talking about that. There is a world movement for sustainable development goals and the use of public statistics for development, for public policy, for public management, or for acting as a citizen. So when empowerment for empowering the society, for understanding the society, and what are the challenges in the sense that how can we that teach or work in statistics help shape a better world, considering all those goals that we have to deal for the next 30 years?
No, I just wanted to add a comment on before on our mission as a statistician. Nowadays, there are a lot of statistical software going around. Many people have data, for example, about efficacy of a drug, push the button, get the p-value, the drug is working, is not working. Or Markov chain Monte Carlo, they push the button, they get an estimate. The point is, are the people able to understand what they have done? So sometimes statistics just push a button and get a result. The point is, as a statistician, we have this mission to explain people that what they are doing, what are the consequences of that, and what is behind that. But apart from that, let's go back to the current question. It seems that big data is something you don't like, because it was question number 3, actually. But we skipped it, but okay, there will be big data. Going back to the ISI, as I said here, I am a council member of ISI. Well, ISI is working a lot with the United Nations in shaping some statistical procedures at world level. So this is an important issue. Also, ISI has another important role about ethics. It has an ethics committee. ISI took position, for example, when the leader of the statistical national offices in Greece and Argentina were somehow fired by the government because they did not want to squeeze the data in a way that the governments liked. So that was, this is an important issue, a mission also of statisticians. So collecting data for the use of the population. I was discussing with Enrico Giovannini. Enrico Giovannini was the president of Italian office, statistical office, and also was a minister for a short while in Italy. And the interest now in official statistics is sometimes in finding an index for a quality of life. So we have plenty of data. That goes back also goes to the big data issue, but we have plenty of data. But out of that data, can we say something about if a life is good for people? What are the problems of the people? So the role of official statistics is definitely important. And as already said before, there are a lot of issues about environment and so on. And just want to bring an experience I had some years ago when I attended a conference in Africa, in Benin, and we are going to have the third conference pretty soon. I went there, I was going to talk about reliability. But then when I was there, I saw what the people were talking about. We were talking about crops, production of the farms, famine. So people, how to feed people, how to increase the production of wheat and so on. So that is something that statistics can give a contribution, working with the real problem of the real people in the world. And I would say these are essentially the goals. Also, another issue that ISI addressed was with Canada. Canada, as far as I remember, decided at some point to stop to collect many data out of the census. The use of the data that people are doing, the governments are doing with the census data is really, really important. And Canada decided to save money in doing that, and ISI took a position. I think the new prime minister in Canada changed a lot about that. So you can see there are a lot of issues between politics and statistics which are really, really important. It's yours.
So this is a bit outside of my area, so I'm really not talking statistically, but Fabrizio makes a very good point, and we've seen this in politics in the United States too. It's not so much cutting back on the collection of data to save money, it's more to cut back on the collection of data because the politicians are afraid of the truth, frankly. That's my opinion, and that's a much more dangerous sort of cutting back in the collection of data.
Yeah, I was brought up as a mathematical statistician, and I definitely used to be very dismissive of official statistics as just people counting measles or something. So, and I've changed my mind completely about this. They're so important for society. I actually think, as Bill was saying, that it's actually an ethical issue. I think this is a deep ethical role that statisticians have to discover what is going on and to present it. And that's their job. And I think in the clearest possible way. So I think it's a wonderful role for statisticians. And official statistics, particularly say for sustainable development goals, where you're working in countries without good statistical sources, is a fascinating, challenging issue. Just how much can be replaced by data from, that you might get from surveys using mobile phones, or which everyone has got, and so on. So there's all sorts of fantastic challenges there, which involve working with data scientists, with working with people with very different expertise, but for which there's always a need for serious statistical input. So it's an area which I used to be very dismissive of, and now I think is both fascinating and vital. So I think again, as was said, is there yet more things to teach? I'm not sure if this is something to teach undergraduate students, but it's things to be used as examples all the time. Many of you will have seen someone like Hans Rosling, the Swedish doctor, who does these extraordinary videos on international development, essentially, which have been very powerful and very give a very strong emotional impact to show how simple, routine, official data can tell extraordinary stories about the world we're living in. And so with that kind of inspiration, I think this is a very important area to work in.
I guess the real challenge we still face is getting respect for our profession, that we can have a useful impact. I would guess I'm probably not the only person in this room who's had the experience many times over the years of meeting someone at a party, telling them what I do for a living, and the reaction is, I had to take statistics once, I hated it, or oh, it was horrible, or you get the sense that the person took a course in statistics and didn't really understand why statistics could be helpful to them, to understand the world around them, to answering some of these important questions and problems we face. So, I think things have improved somewhat. I know just in the U.S., some of the success stories, like Nate Silver in the recent presidential election, his predicting every state perfectly. People have seen some things like that, I guess, in the old days, hearing about Deming. Some people heard about some aspects of statistics working that gave us a bit more respect, but I think we still have a long way to go. There's no easy answers, and part of it relates to what we were talking about earlier, of the issues in teaching the basic statistics courses and having it done in an effective manner. But it's still something we all need to address, how we can have some impact, some respect for our profession, so that we are called upon to contribute with other people and trying to address some of these important problems in the world.
So, is there a comment? Yeah, Nicolette.
Thank you. We are talking about statistics and about how to help and to share a better future for next generations. One very important question is, for example, to try to create a model for terrorist attack. Nobody talks about this. Look, only last month, how many terrorist attacks in France there? Nobody's talking for a model of immigration, which is something also very important. So I think the role of statistics is not only to analyze the data, but the statistician, some statisticians could think about model that can describe the risk model, let's tell, which can predict such unfortunate events. Okay, this is a non-standard way of thinking, but very important, I think. And also, since you mentioned about all these indices which are used in public statistics, and all these indices, there are some numbers. So it's possible, based on this all big data, to try to implement local indices, but not global indices, because we are interested how the people are feeling, but which people, rich, poor, in Syria, in Italy, in Europe. So the indices are not the global indices. They do not tell everything for the real relation. What tells correlation 0.3? Nothing. But you have some local version. This helps to look upside of the things. Okay, thank you.
Regarding the terrorists, let me say something. Well, there are statisticians working on that. What I'm going to present in a couple of days is about adversarial risk analysis. I just got involved in this one, but this is essentially a way in which you have to make a decision in which there are two agents. One is the defender, one is the attacker. It's a game theory, but this is a game theory in which you, defender, the state, are trying to think what the attacker, the terrorists, are doing and trying to find the action which is the best to protect yourself from this attack. There is some work on Somali pirates by my friends, Spanish friends, and so on, so on. I'm also doing some work on using self-exciting processes to describe the occurrences of terrorist attacks. But this is a very, very minor contribution. But I fully agree with you. This is an important area, but we can offer something. Of course, we can also offer something about some decision by the governments. Now, for example, I have to decide if to go or not to Iran. Because if I go to Iran, the United States thinks I am a possible terrorist. Therefore, I need a visa to enter the United States. So should I go to Iran, accept the invitation or not? So we have also, in this example, so it's a very conservative, in many point of view, actions by the government. If I look at the probability, a person like me, what is the threat I can give to the United States if I go to Iran to a statistical conference? That is, so we have also to be careful in using also statistics to avoid actions which are definitely useless, like this one, for example.
I'm very interested in risk models for all sorts of events, but one of the problems is that they are, almost completely misunderstood by the media in that they think they're models to predict what will happen. Which they're not. They're models to give reasonable probabilities for what might happen. So, for example, all of Nate Silver's models for elections just give a probability. I mean, he got the states right, but he was very lucky because Florida was 51-49 and just happened to go his way. So he was very lucky indeed. And so and 538, Nate Silver's organization, is excellent in that what it communicates is probabilities. It doesn't say who will be president. It doesn't predict anything. It just monitors and provides probabilities. And this is very important in areas like terrorism, which are essentially, which are unpredictable. But the odds, you can give reasonable odds, perhaps. So similarly, I mean, the areas where that is well understood is in football and in earthquakes. You cannot predict the result of a football match. You cannot predict when an earthquake might happen or a volcano might erupt. But you can produce, for football, certainly very good probabilities and make money from them. So that's one of the biggest elements, I think, of public education that's needed, in particular media education, is that statisticians do not predict what will happen. They produce probabilities for what will happen. That's actually one of the differences between that and many machine learning models, which do tend to produce classifications rather than probabilities. Not all.
More questions? I just want to add about migration. There are many studies about models and migration and international migration. What is happening now is that it's an overwhelming situation and phenomenon, and of course was not predicted. But now people are, as soon as the same way that there are many methods to do census or surveys or public statistics in areas of war, that is a different way of counting as well, or counting crowns. But yes, we have much to contribute for it. But there are some people in social statistics working with a lot with demographers, and there is a lot to be done. Because we have gone through all our proposed questions and things, I would like to know if the members of the speakers or the audience would like to raise any other question, comment, or topic that want to have it commented or discussed here, and they are all free. So, anyone, any proposal? We still have a bit of time.
Can I say big data? Was question number 3 that you skipped?
Yeah, I think we can go back to number 3, of course. It's the most popular one.
Yes, well, big
so
data.
Feel free.
Let me say something about big data. And well, as a Bayesian, I have a lot of problems with big data because I used to say, We have a limited number of data. We can give predictive distribution that goes into definitive word, or we have a Poisson process with parameter lambda. We try to understand what is the meaning of lambda. That's what I said yesterday in the mini course, and then trying to get information, ask the experts, and so on. So this is the way to go Bayesian, and there has been for last decades, 15 years, a discussion between objective Bayesians and what are called subjective Bayesian, which I would call proper Bayesians. And the point is, because we were claiming it was not possible to give exactly the prior distribution and so on, it was not possible to get an expert. We have to find some ways of giving in an objective way a prior distribution. And they've been fighting against these people. Now that we are going to have plenty of data, plenty of parameters, plenty of everything, how can I ask an expert to assess something about 1,000 parameters, relations between them? That will make my life definitely miserable with respect to these people of objective Bayesian. So that is something that we have to address. I still think that the Bayesian approach can be useful in detecting relations, sparsity. There are many computational issues which are already dealt with by the Bayesian approach. So regarding big data, there are some computational aspects. Many problems nowadays, for many problems, it's difficult to get the proper likelihood. The likelihood is very difficult. So there are ways of dealing with. Now I'm trying to get back to some consideration by the computational statistician here. So are methods like ABC, approximate Bayesian computations. There are methods like indirect inference, which means building a model which somehow approximate the real one and trying to make inference on that model which mimic the actual one. Computer codes mimicking the behavior of complex models. Or now there is a need, as I said in my first talk here, for looking at stochastic differential equation for complex, very complex model. So we have issues which are computational issues, and we have also issues which are in terms of stochastic model. I fully agree with Nikolai that it's difficult to explain what stochastic model is, but that is to be our goal. Also, there are a lot. Now, the big data are providing us a great opportunity, like Bill was mentioning during his presentation yesterday. So something individualized. You mean now, when you go to the doctor, it's possible in the future to get something exactly for you. Looking at the DNA or all the genetic stuff, it's possible to look at that. If you think of an airplane, as Bill was mentioning, you can look at that airplane, not all the 747 and so on. So individualized items, which is something which is brought by this fact that we are dealing with big data. And an important aspect will be also astrostatistics. For the future, I think a lot of work can be done in terms of use of statistical methods in astrophysics. And for example, Bayesian methods have been used about gravitational waves. I'm interested in this one because one of my sons is getting a master in theoretical physics. He wants to study gravitational waves, and that will be a great opportunity for me to work with him and learn sometimes, eventually in my life, something about physics. So you can see there are also neuroimaging. So there are plenty of fields in which now we can use statistical methods, thanks to the fact that we have big data. But we have big issues, computational modeling, and that is a great opportunity to going back to what we said before, for a cooperation with applied mathematicians, probabilists, engineers, and so on. This is definitely something I will keep repeating. We are not alone. We are not the only one who have the truth in their pockets. We have to cooperate with other people and learn a lot. In my life, I learned a lot from engineers. Also learn a lot also about stochastic modeling, working with engineers, because I was able to do something new in my field just by ideas I got from the people I was working with.
So So I have some similar thoughts to express relative to big data. 25 years ago, Jerry Hahn and I published a book on statistical intervals. And not too long ago, I was talking to somebody about the fact that we were doing a revision on that. The revision actually was just finished and delivered back to Wiley just about a week and a half ago. And so this person asked me, he said, well, what is the relevance of statistical intervals in the world of big data? And so I related a couple of experiences that I had. When we've got big data, and we've got a particular question we want to answer, the real issue is how much information do we have in the big data about that question? And so sometimes, even though we've got big data, we've got a small amount of information. And in a situation like that, quantifying your uncertainty, your statistical uncertainty, I should say, still remains a very important issue. Another little story that I have is that I've mentioned before that one of the areas in which I've worked over the years is reliability. And one of the particular problems that I've had some contact with is the reliability of wind turbines. So wind energy is a sort of a growth field because it's sustainable, renewable, and clean. And Iowa in the United States is the third largest state, even though we're small geographically and in terms of population, we're the third largest state in terms of the amount of energy, electricity in particular, derived from wind energy. Well, it turns out that there's been a really serious reliability problem in wind turbines, and in particular the gearboxes in wind turbines are failing massively. They were designed to last 20 years, but they're only lasting 4, 5, or 6 years. And the reason for that is the engineers just didn't understand the stresses. Engineers are pretty good at designing things to withstand certain stresses, but they have to understand the kind of stresses. And so there's been a lot of interest in prognostics, being able to predict the remaining life of these gearboxes. And a statistician that I know that works for an energy company, or a company involved in wind energy, I'll say, told me a story. He said that there was a connection between the group of people who were responsible for the reliability, prediction, prognostics, and a university that had a fairly strong machine learning group in related to computer science. And so there was an agreement between this university and the machine learners there and the company to look at the big data that were being gathered about wind turbines. And there's a lot of big data in wind turbines. There's a whole fleet, a very large fleet of wind turbines, and they're giving data every maybe 10 minutes about how the systems are being used and so forth. And the machine learners were totally unable to make a connection between the failures, that is the ones that failed, the ones that didn't fail, and when they failed, and the big data covariates that were being collected. On the other hand, once you got involved in the data from a statistical point of view, statistical thinking and mechanistic thinking, where the engineers get together and identify, gee, what were the failure mechanisms? Well, first of all, what were the failure modes, which is what the technician writes down that caused the failure, and then the mechanisms, which would be sort of the physics of failure, cracks growing or other materials phenomena going on due to things like creep and so forth. So these are the mechanisms that ultimately lead to failure. And so when the statistician and the engineers got together to figure out what caused the failures, and then what are the things that mechanistically are leading to the failures, the mechanistic things being like amount of use, the amount of load, and the shocks, the mechanical shocks that were being seen over time, they were able to get a very good relationship that would then allow the prediction of future failures. So machine learning, now I don't know, maybe the machine learners that were doing this were incompetent, they didn't know what they were doing. I don't know those details, but what I know is when they were trying to apply standard machine learning techniques, they were unable to come up with anything. So I think that statistical thinking and sort of mechanistic thinking, bringing in our knowledge about what's going on in the background with different mechanisms, that combination is very powerful to extract the limited information in big data.
But it's interesting because there are examples that go the other way. When you've got masses of data and actually you don't use subject matter expertise. The hedge fund that pays me don't employ any economists. They do it purely on data analytics. The Connect system that reads your movement, Microsoft, when you're playing tennis against the computer, doesn't use any knowledge of the body and how it works, the ergonomics. It's based purely on a machine learning algorithm. Natural language processing doesn't use good programs to do that. Don't use any knowledge about linguistics or the structure of language. Google Translate just uses purely statistical, almost knowledgeless abstraction and association to do its translation. So So what's interesting is, of course, is to try to identify which areas an absolute black box. It's statistical machine learning, but it's not using any real substantive knowledge. Where that works and where actually you really have to have subject matter expertise, and trying to identify which area is which is very important.
Yes, that's an interesting observation. I wonder, as David was speaking that, I was wondering if one issue that might differentiate between these two different situations might be, are we talking about sort of central tendency, or are we talking about things in the extremes? Because certainly in terms of gearbox reliability, it's the extremes that are driving the failures. Getting into the tails of the distribution. Now, sometimes we can do that empirically, but a lot of times we're extrapolating. And when we need to extrapolate, the interpolation that the machine learning algorithms typically provide are not going to be sufficient.
Just to add to the discussion we had here yesterday, and with two short talks about the big data and official statistics, because there is also this discussion that, oh, we won't need more official statistics or public statistics or survey methods to do to take social or economic indicators, and there is this example that Bob Groves gave, that is, you have this idea that one of the problems with the big data for the social surveys or official statistics is that you don't know what's missing. So when you are used to do survey, we used to have non-response, and then because the survey has, the sample has been selected, you know which households didn't respond, or you know which enterprise didn't respond. When you want to get some official public statistics or social indicators for any type of big data, the problem is you don't know who is not there or who is duplicated. And then you have to infer about non-response and doing imputation, have no information about who and what is missing. So, but we know that what we need to do is to learn and to use combined modes of in the future, also for official statistics. More issues, more comments? Yes.
Thank you. Building a bit on what you just said, we often hear about big data and so much data that is available, and statisticians should analyze this data and tell us something about it. Okay, so there's some some sort of pressure on statisticians that now you have data, data is there, now tell us something. And I hardly ever hear people discussing about the quality of this data. What can we say about data that often we don't know where it came from, how it has been collected? Is this data, what was is there some sampling techniques that have been used? What control is there for cross effects from other things? How can we expect statisticians just to apply some methodology or to use some models and then make predictions or even just calculate probabilities based on data that we don't know which value they have? And what can statisticians do, and what message can statisticians give to the outside world, to the public domain, to say that just having data in any way is not the answer and is not the way and will not provide information, that some control, some filter should be used. So not any data is good data.
I think if anybody just takes some, as people say, found data and applies a statistical technique and comes up with, calculates a confidence interval, then they are being a very, very bad statistician. This is not good statistics at all. And it's something that somebody with a little bit of learning might do, and it's completely inappropriate. So, but they may, of course, use the package correctly, but you can't believe the numbers that come out. So I mean, that's where real statistical expertise comes in, which isn't just to do with knowing about regression and how confidence intervals arise, because almost certainly those intervals are wrong. So the real statistical expertise is saying, okay, this package has come up with this confidence. I don't believe it. The sources of bias are much bigger than the stochastic error that's expressed in the interval. And that's difficult because you're saying that actually you can't learn what you want to learn from this data. But that's always been the role of the statistician in early, in a way, before they got control of agricultural, experimentation, they were dealing with people. And in medicine, 50, 60 years ago, a doctor would try out some, his treatment on a few patients and then say, analyze that. Well, you just got to say, well, no, no, I won't, shan't. And things have changed. In medicine, it completely, such, attitude is unacceptable now as medicine. Unfortunately, of course, it's coming back because people say we can use, well, in medicine, it's called real world data. Yeah. That's the phrase, which of course sounds wonderful. Who would not want real world data? But actually, it's much better called found data, because then it looks like something you've just picked up in the street, which is the correct, I think, image for it.
There is also another expression that people are using is organic data, because it's a subproduct of a big system of process. Yeah. And we will need to deal with that, but understanding what it is.
Only observation in relation with your extreme value behavior of the process. It's well known that, let's say, Gaussian couple has zero tail dependence index. Also, somehow, many years ago, they thought that the Gaussian couple was the reason of finance crisis, 2008. But what happens recently, very recently, that there are studies which show that the Gaussian couple, which measures how to say the upper tau dependence index of the Gaussian couple is not always zero. If you consider the index as a coefficient, it is zero. But if you consider it as a local measure of extreme dependence, it is not zero. So my observation is the following, that somehow we statisticians have to revise the facts which are implemented to the engineers, to economists, etc., in terms of interpretation, because the Gaussian couple is something good, but not the real reason of financial crisis. This was only observation in relation with the extreme value behavior of the processes. And this result is very recent. This will appear just in econometrics this year.
There is a question for Professor Michael Kosarak.
I wanted to just go back a little bit to the education question. My wheels were turning kind of slowly, so I'm a little behind here. But the question that was raised was, how do you deal with such a quickly adapting world when we only have a finite amount of time to learn or capacity to learn? And I just had a couple thoughts on that. One is to do with how we would go about graduate education, the kind of goals we should probably shift towards. And this may not work for everything, but it may be helpful. So I've tried, as chair of our department and in consultation with our faculty, tried to focus our master's degree on giving statisticians and biostatisticians, in our case, the framework, some basic tools that will be useful, but the ability to learn essentially any of the major tools. So talk about hierarchical models instead of, for example, structural equation models, since one's a special case of the other, and give them general principles. And our students were able to, in many cases, to go into a situation where they hadn't actually taken a structural equation modeling course, but they learned it within a week or two and were able to work with the software because they had principles underlying there. So I think we need to think about our overall goals. So for the master's level, I would say the goal should be they have the capacity to do a few things well already right out the door, but to learn anything new in a couple weeks. That would be what we would want them to be able to do. And then for the doctoral level, you want to have enough of, they should have the master's level training, but you want to have enough foundational thinking, whatever that means. We have to work at maybe making that sufficiently broad so that they can also get into any new area and make intellectual contribution in a relatively short period of time. Not 2 weeks perhaps, but maybe a couple months, so that their collaborators that come to them say, I've got this issue, it's completely different. And they'll say, well, that doesn't even make sense from a sampling space point of view. Well, that shouldn't stop us from working with them and figuring out what we need to if our foundations are broad enough. And it's not, the other thing is it can't be done as individuals. I think groups learn better than individuals learn, especially if the groups are coordinating well. So in some situations in the United States and other places, you have a laboratory-like structure where you have a bunch of students and faculty working together, and they're assigned different things to teach each other. And so over the course of a short period of time, they might learn a lot of new areas that come up from their collaborative and sharing ideas. So I think there are ways we can change the way we approach learning so that we can be adaptive. But I think we have to not take the panic approach where you try to learn everything quickly, superficially, and then you cause a multitude of disasters by doing that. We have to really be, I think, proactive in how we think about that. So that's just one perspective, I think, on the educational question.
More comments? Yeah, Enrico.
I want just to return to the engineering situations that Professor Mike and Professor Cherry just mentioned. I got a degree in engineering, even though it was a long time ago. And after I got my PhD in statistics, I was keeping harder to get closer to the engineers in order to put statistics in action with the people in engineering. And I have to say from my heart that I had no success at all in this task. And because I believe it's kind of harder to get close to the engineering. And the examples that Professor Meeker say about the Gucci and Professor Rucheri said about the Six Sigma program, I believe they was successful among the engineers as far as I know. And I believe the big reason of this is that Taguchi was an engineer, and the people who created the Six Sigma that was just not exactly statistics 101, but some basic concepts of statistics, they brought and the engineers got these concepts, I don't know, in some way that was friendly to them. So in this way, I would like some comments. How do you guys got closer to the engineer in order to make the use of statistics to them?
Yeah, so I can make a couple of comments about that. So Fabrizio did raise the Six Sigma question, and I have a similar sort of perspective on it, but yet different. Um, since I was in graduate school, I was an intern while in graduate school at General Electric Research, and I've kept my contacts there at General Electric ever since. And I can remember I was visiting one summer, and I was hearing from the people in the statistics group before it had been announced publicly that GE was going very much in the Six Sigma direction. And of course, all of that is history now, but I was hearing it before anybody knew about this. And the statisticians told me, we have nothing to do with this. This is all being done without any consultation from the statisticians. Jack Welch made this decision at the top level, and all these consultants are going to be teaching all these courses and on and on and on. Eventually, the statisticians were brought in because it was recognized that people at GE are very smart, and they recognized that precisely what the consultants had was not sufficient for GE, and that they would have to take these concepts and ideas of Six Sigma and customize them for the different parts of General Electric. Certainly the methods that were needed for GE appliances and GE aircraft engines and GE finance are all going to be different. And so the statisticians were brought in to help customize that and to help design some of the training courses. So eventually the statisticians played a very important role. And of course, it was well known that there was not going to be any Six Sigma wars within GE. Like I mentioned, the Taguchi wars. And the reason was that this came top down. Jack Welch said, you will do this. And so the statisticians had to figure out how to adapt and be most valuable, add value to the Six Sigma program within GE. And of course, it turned out to be phenomenally successful. Now, some debate about why it was phenomenally successful. In fact, I remember I gave a talk here at the Sinapi somewhere back around 2000 or thereabouts, at the time where GE had done, and I gave a talk a little bit about Six Sigma and what effect it had, particularly on GE, because this is before Six Sigma had gone very broadly. Everybody was looking at GE. And I remember I had the slide that I put up sort of showing the improvement in the stock price of GE. And it was improving very steadily throughout the 1980s and 1990s. Until you got to 1996, which was the year after it was implemented at GE, and then it went like this. It was just strikingly, now of course part of that was just the state of the economy was improving, so it was a little bit confounding. The other part was that Jack Welch said, you will make this successful. And so people worked really hard to make Six Sigma successful. And when I talked to my statistical friends at GE, they said, well, of course Six Sigma can be successful. Why? Because you're applying basic statistical methods to solve engineering problems. And he said, and moreover, there's a huge amount of what we call low-hanging fruit, where you can make big improvements just by doing some simple optimization. You know, you understand the problem by running experiments, and then you figure out how to optimize it. And so it's not surprising that they were able to get big gains. Of course, the other part of it is that Jack was looking for big gains, and so they found big ways to make big gains. And another observation that my statistical friends at GE told me was that the Six Sigma thing really changed the culture of thinking at a management level. Previously, you'd go into a meeting with management, and all of the discussion was about dollars. some sense, I went to a couple of these, and somebody described it to me what, how the managers are thinking at these meetings. The managers have a bunch of money, and they're sitting there trying to figure out where to place their bets. Which projects are going to get funded and which won't. But what changed was that management, up and down, began to have a real appreciation for variability. And so you'd see managers asking questions. Well, why is there so much variability over here? Because that was just the way Six Sigma taught people to think. And it wasn't just the engineers who were studying Six Sigma. It was all up and down the line. Everybody had to have this basic training. So everybody, managers in particular, big change, were understanding variability. So that's what my statistics friends told me was the biggest change that they saw within the company.
Well, I've been working with some engineers, but some of the work with the same engineers. So I've been lucky. So that is one of the scientific explanation. The other one is that in Italy we have two major technical universities, Politecnico di Milano and Politecnico di Torino, and both of them have a department of mathematical engineering. So mathematics and statistics is taught within the engineering faculty by people who have a degree in mathematics, a degree in statistics. So there is a quite diffuse mathematical knowledge in many departments in mechanics and so on. So there is this sort of attitude within university of accepting working with mathematicians. The problem is when you go out, the engineers are better to sell themselves. We were more successful with the appliance company I mentioned earlier because we proposed quality control charts. When we went to another company proposing non-homogeneous Poisson processes, no, it didn't work. So there are a lot of problems. I agree. So it's difficult to work. But when we worked recently with a major Italian oil company about project management, showing that Bayesian methods were better to improve the estimate of the time to completion of a project, then that was quite successful. So we saw them, they are working in this direction. So you have to do something that they can understand, essentially the company, and understand the methods, especially understand also in terms of return, which might be money or not only money. But it's a difficult task. I have a similar experience like yours.
So I'll make one more comment about the specific question that you asked, and it's close to what Fabrizio has mentioned. What we find is that historically in the engineering sciences and in the physical sciences, the scientists are good quantitatively, and often those scientists and engineers have a sense that it's a showing of weakness if they have to go to a statistician to get advice, because they should know how to do it themselves. And largely, in many cases, they can do things reasonably well, has been my observation. Engineers are very smart, they're good quantitatively, and often they can get to a reasonably good solution just working by themselves. But they've got a lot of limitations as well. One of the big limitations that I've seen in engineering analysis relative to a statistical analysis, which really often is a combination of engineering and statistics, is that they aren't very good at quantifying uncertainty and dealing with probabilities. Historically, most engineering models were deterministic because they didn't understand how to bring the stochastic elements into their models. A lot of that has changed. I remember watching from a distance a whole big program that sort of came through in many areas, but particularly the design of aircraft engines. And historically, it's all been very deterministic with huge safety factors so that the engines, that's the way they can get away with being deterministic, is they build in these huge safety factors. But there was a big push for what was called, and still is called, probabilistic design. Some of us got very nervous about this, that, oh, you're going to replace the big safety factors with probabilistic design. But the way the engineers explained it to me, no, that's not what we're going to do. We're just going to figure out where we need the big safety factors so that we can be more efficient, both in an energy kind of way, but also in an economic way of doing things. And but there is now today, in the last 20 years, a lot more probabilistic design on the engineering side. But before I was contrasting, the sort of the mindset of physical, chemical, and engineering sciences versus the social sciences, where they admit that, gee, I'm a sociologist, I don't know anything about math, help me with my statistics. And so, that's why there's been this difference. But on the other hand, once we can show our value to the engineers, but it's not easy, as you pointed out. But I've been lucky enough to have had a fairly substantial number of collaborations, both with engineers in industry and also engineers in our engineering college at Iowa State University, where they know what I can bring to the table. And so I often will get invitations from the engineers to join a grant proposal because they recognize that what they're doing is highly statistical, and those evaluating the proposals will often recognize that, and then they're favorably impressed when they say, oh, they've got a statistician who can actually do the work. And so I think that in many cases, this approach will lead to more success for the engineers in getting funding for the research that is sort of statistically focused.
I think as statisticians, it's useful if we all have a few simple success stories we can relate to people quickly and easily when we meet someone at a party and we hear their negative reaction, or when we're teaching basic statistics, maybe it is more important to give some success stories to make them understand why it's important. Focus on that more than on the formula for a t-test or whatever. But I think we've all had experiences in our careers of seeing success stories, and it's something we need to be able to advertise readily to other people to help them appreciate what we can bring to the table.
We are approaching the end of the session. I just would like to know if any of the speakers would like any comment, or we are tired enough that you have been, well, Alan has been teaching, some of you have been teaching since 8 o'clock. So what I will do then is to thank you all for this great session and for being here, and for the audience for being here with us, to the Brazilian Statistical Association for providing the suggestions. Was Vera who contacted the ISI and said, so can we have a session that is motivated by ISI and the Brazilian Statistical Association? And for you that are here, that accepted that invitation on top of you have been doing the conference and meeting people, because it's an extra opportunity that we have with you to knowing about your thoughts about statistics and the world.
Sorry, can I make a final suggestion? Okay, when you're at a party and someone says, what do you do? You should flip a coin, and if it comes up heads, say you're a statistician, and if it comes up tails, say you're a data scientist, and see how quickly they move away from you towards the food and the drinks. So, and I wanted an evaluation.
So thank you very much, everybody.